This is a hands-on class, so open the lab guide and expose a deployment alongside me. Over the last 2 classes you learned pods and deployments and end-to-end, how Kubernetes runs your application as a set of disposable pods and keeps them healthy. But that leaves a glaring problem, and it is one you must solve for any real application. Remember 2 facts we established. Pods are ephemeral, and every time a pod is recreated, it gets a brand new IP address. So imagine you have a deployment running 3 pods of your web application. Their IP addresses are constantly changing as pods die and are replaced, and there are several of them, not one. Now, how does anything an 8212, a user, another service, a load balancer and 8212 actually connect to your application? You cannot hardcode a pod on T9 SIP because it will change. You cannot pick one pod because it might die and you would ignore the others. You need something stable and singular in front of your ever-changing herd of pods. No, that something is a service, and it is one of the most important objects in all of Kubernetes. A service gives you one stable address and name that always routes to your healthy pods, load balancing across them, no matter how they come and go. Today, you will learn what a service is, how it finds its pods with labels, how it load balances, the different service types, and how pods discover each other by name. Let us give your pods a front door. Here is our path for today. First, why services are needed. Second, what a service is. Third, the label selector. Fourth, load balancing. Fifth, the service types. And sixth, service discovery by name. Let us dive in. Let us feel the problem sharply first. Because the service is a direct, elegant answer to it. You have a set of pods running your application N82112. Say 3 of them, each with its own IP address on the cluster network. Right away, there are 2 difficulties. First, there are several pods, not one, so NA8221, the address of the app N8221, is not a single thing, N8221 to A21. Which of the 3 do you talk to? And second, and worse, those addresses are not stable. Because pods are ephemeral, any pod can die at any time, and when the deployment replaces it, the new pod comes up with a completely different IP address. So the set of addresses is constantly shifting underneath you. The IP you connected to a minute ago may belong to a pod that no longer exists. Replaced by a new pod at a new address you have no way of knowing in advance. Building anything on a specific pod in 39 SIP is building on quicksand and 82112. It will break the moment that pod is recreated, which happens routinely. So, the question N8200, how do I reliably reach these pods, N8221, has no good answer at the pod level. You cannot hardcode an IP because it changes. You cannot manually track which pods are alive and what their current addresses are, because they change too fast and too often. Anything that needs to talk to your application, an 8200 FAF, a user and SAS browser, another microservice, a load balancer and 8200 FAF, needs a stable, single point of contact that does not care which specific pods exist right now or what their addresses are. It needs an address that stays constant even as the pods behind it churn. That stable point of contact is exactly what a service provides, and it is why services exist. Without them, the disposability of pods that makes Kubernetes resilient would also make it impossible to connect to. So the takeaway, you have several pods, not one, and because pods are ephemeral, their IP addresses change every time they are recreated, NA212, so you can never hardcode or track a pod in 39 S address. To reach your application, you need a stable, single point of contact that stays constant as the pods behind it churn, which is exactly what a service provides. Let us define the service and see how neatly it solves that problem. A service is an object that provides a single, stable virtual IP address and A212 HOV and a name and A200 POV that sits in front of a set of pods. This address does not change. Once you create a service, its IP and name stay constant for the whole life of the service, no matter what happens to the pods behind it. So you finally had the fixed point of contact you needed. one unchanging address that represents your application as a whole, rather than any individual, mortal pod. The service is a stable abstraction over an unstable set of pods. Here is how it works in use. Clients and 8112, whatever needs to reach your application, and 8112 connect to the service and 8112 stable address, not to any pod directly. The service then forwards each incoming request to one of the healthy pods behind it. The client never needs to know how many pods there are, what their addresses are, or which ones currently exist. It just talks to the service, and the service handles delivering the request to an actual live pod. All the churn of pods appearing and disappearing is hidden behind that one steady front door. So the mental model is that a service is a stable front door to a changing set of pods. Behind the door, pods are constantly being created and destroyed, getting new addresses, scaling up and down, and A2, A24. But the door itself, the service, stays in exactly the same place with the same address, always leading to whatever healthy pods happen to exist at that moment. This decoupling is profoundly useful. The things that connect to your app are shielded completely from the internal churn of pods, and your app can scale, heal, and update freely behind the service without anything on the outside needing to change. The service turns a herd of disposable pods into one reliable, addressable application. That single idea makes networking on Kubernetes tractable. So the takeaway, a service is a single, stable virtual IP and name that sits in front of a set of pods and never changes, and A202 hull. Clients connect to the service, which forwards each request to a healthy pod behind it, and A2112, so it is a steady front door that hides all the churn of pods, turning a changing herd of disposable pods into one reliable, addressable application. A natural question follows: how does a service know which pods it is in front of, given that those pods keep changing? The answer is elegant, and it reuses something you already know: labels. A service does not track its pods by their IP addresses, and A212. That would be impossible, since they change. Instead, it identifies its pods using a label selector. Recall from the object model class that pods carry labels and AT104. Simple key value tags like an AT120 app equals web and AT120. A service is configured with a selector that says, in effect, an AT120. My pods are all the pods with this label. A service might select all pods labeled app equals web. It defines its target group by a property, not by a fixed list of addresses. The beauty of this is that it automatically tracks the changing set of pods. Because the service selects by label, whenever a new pod with the matching label appears, an A212, say the deployment scales up or replaces a dead pod, an A212, the service instantly includes it, since it too has the label. And when a labeled pod disappears, the service simply stops sending to it. The service always points to exactly the current set of pods that match its selector, with no manual updating. The label selector is the living link between the stable service and the churning pods. As pods come and go, the selector re-evaluates and the service and thus targets update themselves. And this is precisely why it works so well with deployments. Your deployment creates pods, all carrying the same label and A212, app equals web and A212, and your service selects that same label. So the service automatically fronts exactly the pods your deployment manages. And as the deployment heals and scales those pods, the service follows along effortlessly. This is the label and selector mechanism from the object model doing real load-bearing work. It is how a stable service stays correctly connected to an ever-changing set of pods without anyone having to wire up addresses. The lesson is practical to an 8-high-12. Your service in 99, selector must match your pods in 39. Labels exactly, or the service will front no pods in traffic will go nowhere. Get the labels right, and the connection is automatic and self-maintaining. So the takeaway, a service identifies its pods by a label selector, an A2012, and A2020. All pods labeled app equals web and A2020 2021, and A2012, not by fixed IPs. So as matching pods come and go, the service automatically tracks the current set. This label and selector link is how a stable service stays correctly connected to the churning pods a deployment manages, provided the selector matches the pods in 3.9 labels exactly. A service does not just find the right pods and 812, it also distributes traffic across them intelligently. This is its load balancing rule, and it should feel familiar from the cloud classes. When requests arrive at the service, and there are several pods behind it, the service spreads those requests across all of the healthy pods rather than dumping them all on one. Each incoming request is sent to one of the pods, and over many requests, the load is balanced roughly evenly across the group. So your 3 web pods each handle their fair share of the traffic, and no single pod is overwhelmed while others sit idle. The service acts as a built-in load balancer for the pods it fronts. Crucially, the service only sends traffic to healthy pods, and it automatically stops sending to any pod that has died or become unready. Kubernetes tracks which pods behind the service are alive and ready to serve, and the service routes only to those. The instant a pod fails, the service takes it out of rotation, so requests are never sent to a dead pod and left to timeout. Combined with the self-healing from the deployment class and 8212, which replaces the dead pod and 8212. This means failures are handled seamlessly. The deployment brings up a replacement, the service and 8209. Selector picks it up, and traffic flows on, all automatically. So the service gives you load balancing and availability together, for free, just by existing in front of your pods. Requests are spread evenly for good performance, and dead pods are skipped for reliability and 8212. Exactly the load balancer behavior you learned about in the cloud, now built directly into Kubernetes at the service level. You do not set up a separate load balancer for your internal pods, the service is one. This is a big part of why services are so central. A single object gives your pods a stable address, automatic membership by label, even distribution of traffic, and automatic avoidance of failures. It quietly delivers the reliable, balanced front end that every real application needs. Put a service in front of your pods, and they become a robust load balance group instead of a fragile set of individual addresses. So the takeaway, a service load balances by spreading incoming requests across all its healthy pods rather than one, and it automatically stops routing to any pod that has died and 821.281. So combined with the deployment and 209 self-healing, failures are handled seamlessly. The service delivers even traffic distribution and availability together, a built-in load balancer for the pods it fronts. Not all services are meant to be reached from the same place, and 82112, some are internal, some public. Kubernetes captures this with service types, and knowing the 3 main ones is essential. The default type is cluster IP. A cluster IP service is reachable only from inside the cluster, and 8212, it gets an internal virtual IP that other pods and services within its cluster can use, but nothing outside the cluster can reach it. This is exactly what you want for internal components, a database, a backend service, anything that should only be talked to by other parts of your application, never exposed to the outside world. Most services in a typical cluster are cluster IP because most components are internal. It is internal by default, which is the safe default. The second type is node port. A node port service opens a specific port on every node in the cluster, so that traffic arriving at any node on that port is forwarded to the service and onto its pods. This makes the service reachable from outside the cluster via node in 1039 address and that port. It is a simple way to expose something externally, often used for development or basic access. Though it is fairly low level and 812, you are exposing a raw port on your nodes. It is a step from internal only toward external reach. The third type is load balancer. A load balancer service asks the cloud provider to provision a real external load balancer with a public address sitting in front of your service. This is the standard way to expose a service to the internet in the cloud. You get a stable public IP or hostname backed by the cloud and Tiny9's own load balancer, distributing traffic into your service and its pods. It is the production way to make an application publicly reachable. So the 3 types form a spectrum of exposure: cluster IP for internal only, node port for a basic external port on the nodes, and load balancer for a proper public address from the cloud. You choose based on who should be able to reach the service, and 82112. Keep internal things cluster IP, and reach for load balancer only when something genuinely needs to face the world. Matching the type to the intended audience is a key design decision, and defaulting to internal keeps you secure. So the takeaway, service type set who can reach a service, and 80212 cluster IP, the default, is reachable only inside the cluster and right for internal components. Node port opens a port on every node for basic external access, and load balancer asks the cloud for a reach public address. The production way to face the internet, and 80200, so choose the type by the intended audience, keeping things internal by default. There is one more piece that makes services wonderful to use. You do not even need to know a service NAIS IP address, because you can reach it by name. This is service discovery, and it ties back to last class N18S DNS. Kubernetes automatically gives every service a DNS name within the cluster, and 82112 typically just the service N29S name. So a pod that wants to talk to, say, the web service does not need to look up or configure the service and SIP address at all. It can simply use the name and 80200 web service and 80200 as the address, and it will reach the service. The name is stable and human-friendly, tied to the service, and it works from any pod in the cluster. You refer to services by what they are, not by a number. Under the hood, this works through DNS. Exactly as you learned last class, and 80200 twofold, Kubernetes runs its own internal DNS for the cluster. When a pod uses a service at the name S-name, the cluster DNS resolves that name to the service at the name S-stable virtual IP address, and the connection proceeds from there. It is the same name to address translation as the wider internet, and D39S DNS running privately inside your cluster for its services. So the DNS concepts you just learned apply directly here. Names are resolved to addresses automatically, so humans and code can use memorable names instead of numbers. This is what makes building multi-service applications on Kubernetes so clean. Your front-end pod can talk to a N82020, backend N8202021 service by name. Your backend can talk to a N820 database N8202021 service by name, and none of them ever hard codes an IP address. Everything refers to everything else by stable, meaningful names, and the cluster NT SAS DNS resolves those names to the current service IPS, which in turn route to the current pods. It all composes beautifully. Pods are found by services via labels, and services are found by other pods via names. The result is that your application is a web of named services that automatically discover and connect to each other, resilient to all the underlying churn of pods and addresses. That is service discovery, and it is the final piece that makes Kubernetes networking feel effortless. In today and 30 and 39 S-Lab, you will reach one service from another pod using just its name. So the takeaway, Kubernetes gives every service a DNS name, so a pod can reach another service just by its name rather than any IP and 80212. The cluster in 3T9's built-in DNS resolves that name to the service and S-stable IP. Exactly like the DNS you learned last class, and 821 which lets you build applications as a web of named services that discover and connect to each other with no hard-coded addresses. Let us assemble the whole picture, connecting services to the pods and deployments you already know. You have a deployment running your web application as several pods, all labeled app equals web, and the deployment keeps them healthy, replacing any that die and scaling them as needed, and 812 pods coming and going with ever-changing IPs. In front of them, you create a service with a stable IP and name and a selector of app equals web. Immediately, the service adopts exactly those pods because their labels match its selector. You now have a fixed front door to a dynamic set of pods. Now traffic flows cleanly. A request and 8200 dwell from another pod using the service and 39S name, or from outside if the service is a load balancer and 8200 dwell arrives at the service and 39s table address. The service load balances it across the healthy web pods, sending it to one of them to handle. The client neither knows nor cares which pod served it, or that there are several, or that they keep changing. It just talked to the service by its steady name and got served. All the complexity of the churning pods is hidden behind that one stable service. And when a pod dies, everything self-heals without a ripple. The deployment notices and creates a replacement pod, which comes up with the app equals web label. The service end by V as selector immediately includes the new pod and drops the dead one. So traffic keeps flowing to healthy pods throughout an 80-100 down. The failure is invisible to clients. This is the full Kubernetes networking picture. Deployments keep the right pods running. Labels connect pods to services. Services give a stable address and load balance across the pods. And DNS lets everything find everything by name. Each object you have learned plays its part, and together they turn a set of disposable containers into a reliable, reachable, self-healing application. That cooperation is the elegance of Kubernetes, seen whole. So the takeaway, it all fits together. An 8212, a deployment keeps labeled pods healthy. A service with a matching selector gives them a stable address and load balances traffic across the healthy ones. And DNS lets clients reach the service by name and 8212. So when a pod dies, the deployment replaces it and the service instantly re-includes it, keeping the application reliably reachable and self-healing behind one steady front door. Let us close with the habits that make services work smoothly in practice. First and most important, never connect to a pod in 29 SIP directly and 8112. Always go through a service. This is the whole point. A pod IP is temporary and will break your connection the moment the pod is recreated. A service IP or name is stable and always routes to healthy pods. So, whenever one part of your system needs to reach another, it should target a service, never an individual pod. Make an 82020. Talk to services, not pods in 821. An ironclad rule, and a whole class of fragility disappears. Second, keep your labels and selectors aligned. A service finds its pods purely by label match. So if your service in TNI selector and your pods in TNI labels do not correspond exactly, the service will front no pods at all and traffic will silently go nowhere and A212. A common and confusing beginner bug. So label your pods deliberately. Set your service selector to match, and when a service seems to have no endpoints, check the labels first. The label match is the load-bearing connection, so treat it carefully. And third, choose the service type by audience, defaulting to internal. Use cluster IP and 821.12 internal only and 821.12 for everything that does not genuinely need to face the outside world, which is most things. Reach for node port or load balancer only when a component truly must be reachable from outside the cluster. Defaulting to internal keeps your application anti-SANI surface small and secure, exposing only what must be exposed. Go through services, not pods, keep labels and selectors matched, and default to internal exposure and 82112. Those three habits make Kubernetes networking reliable and safe. In the lab, you will put a service in front of a deployment and see all of this work. So the takeaway, 3 habits make services work well and 8112. Never connect to a pod IP directly, but always go through a service since pod IPs are temporary. Keep your service selector matched exactly to your pods in 39, labels or traffic silent key goes nowhere. And choose the service type by audience while defaulting to internal cluster IP to keep your application secure. Let us gather the whole class in one breath. Services exist because pods are ephemeral and their IPs change, and 82112, you need a stable address in front of them. A service is a stable virtual IP and name that sits in front of a set of pods and forwards to them. It finds its pods by a label selector, not by fixed IPs, so it tracks the changing set automatically. It load balances requests across the healthy pods and skips any that have died. Service types set the audience and 824, cluster IP internal, node port a node port, load balancer a public address. And service discovery lets pods reach a service by its DNS name. via the cluster NE39 S built-in DNS. Next class N8N1 Ingress, routing outside traffic to your services. One idea at a time. That is the service and